Of the fourth workshop. And this session will be about gravitational wave and astrophysics. And our first speaker will be Professor Donghui Jeong from Penn State and TIAS, and he will tell us about dark matter black holes from LBK gravitational wave detectors. So please go ahead.
Okay, thank you. Thank you for the invitation. And today I'll tell you about the gravitational waves and how we can use the gravitational waves to study dark matter properties. So this talk will be a little bit different from the main theme of the conference in a way that you guys are interested in having the first principle theory about gravitational, the dark matter. I try to find out a phenomenological evidence of the property of the dark matter from the new observable, namely the gravitational waves. Okay, let me start from this pie chart, just to remind you that the 95% of our universe is unknown. That's why we are all here to study and wondering about the property of dark matter and dark energy. And using this component of the constituent of the universe, we can reconstruct the expanding history from very early on, from the Big Bang or inflation to right now. So as an astrophysical cosmologist, my job is to answer those fundamental questions about the nature of this dark matter, dark energy, and the inflation from the observables, right? So among them, I'll try to focus on the dark matter today. I'll first summarize astrophysical properties of dark matter. So what you know about dark matter, and then what are the astrophysical constraints of dark matter. Historically, dark matter was detected, or the idea of dark matter was first conceived by Zwicky in 1932. And what's shown here in the left-hand side is a coma cluster. So that's the bundling of many galaxies. Essentially, all dots that you see here, they are clustered galaxies. And then those galaxies are clustered together in this part of the sky. That's what we call the galaxy cluster. If you look at the sky map in the galactic plane, this is galactic coordinate because in the equator we have galactic plane. The coma cluster is located right on these nerves. That's the coma cluster. That's about 100 megaparsecs away from us. Okay, so Zwicky was not an observer; he was a theorist, and what he did was looking at those numbers. And these are the summary numbers about this coma cluster. And then he found something very weird. So in this figure, we have about 10,000 galaxies. And then the size of this figure is about 6 megaparsec. And then the crossing time of those with these velocities per 1,000 kilometers per second is about 6 times 10 to 9 years, which is obviously smaller than the age of the universe. Means that it's very rare that those 10,000 galaxies get together at one part of the sky just randomly, right? And then if we take all the masses that we see, the stellar mass is about 3 times 10 to 13 solar mass, and comparing, and then he can calculate, given mass and the radius, the escape velocity. And the escape velocity he calculated was 140 kilometers per second. That was the mystery because galaxies are moving with 1,000 kilometers per second random velocity, which is far greater than the escaping velocity. So that was the first clue about dark matter. And then he surmised that, okay, if we are to explain the fact that those 10,000 galaxies are put together with gravity, we need about 98% of missing matter. Missing matter means invisible matter in that cluster. So that was what happened in 1932. But that discovery was largely ignored for about 30 or 40 years, mainly because of some personal character of Zwicky. But then later in the 70s, Vera Rubin made a discovery, and she made a discovery with this dot in the optical image. So this is optical image, again, in the galactic plane. So I'm highlighting this dot here. That's the location of Andromeda galaxy, which looks like this. And this is a galaxy, a very nearby galaxy, about 1 megaparsec away. And what Vera Rubin did was she was focusing on individual galaxies, individual stars in the galaxy, and then figure out the rotational velocity around that galaxy, right? And then as a function of radius from the center, so she charted the rotational velocity, moving one direction here, another direction there, and then she figured out that this velocity rotational curve is flat, right? And later we extend this diagram to the further distance. And then another interesting object is this one. And you may not see anything if depending on your resolution, but this is a location. I mean, this was Andromeda, right? This was a location of another galaxy called M33. That is the third largest spiral galaxy in our local group. And around this galaxy, we have focused on individual star and then measured the rotational velocity of the star as a function of radius. And then this is the result. And the yellow line is the rotational velocity of star. And then further out, we also measure the rotational distance, rotational velocity using the neutral hydrogen, using the 200 centimeter hyperfine transition line. And then that's what it found. So that's the dynamics of star and the gas around the galaxy. And if you, on the other hand, if you take all the mass that we can observe and then calculate the rotational velocity based upon the visible mass, and the dotted line is what it has. So clearly we see the gap between the rotational curve that we measure and then the rotational curve that our theory of gravity, named Newton's law of motion, dictates. So then the gap between them should be explained by invisible mass. Okay. And I show you the rotational velocity of Andromeda and M33, and there are numerous other galaxies in our local group. So this is about 1 megaparsec size pie chart. I mean, not pie chart, the cylindrical chart of local object. So here we have Milky Way. This is Andromeda galaxy, and M33 is here. Around our Milky Way and Andromeda galaxy, there are small galaxies, so-called dwarf galaxies. And those four are the examples of dwarf galaxies in the Fornax and Sculptor and Carina and Sexton. Those are the constellation name that these dwarf galaxies are seen in our night sky. And what you can see here is the individual dwarf galaxy can be reserved in star by star manner. So what you can do is we can measure the dynamics of individual star to study the total mass inside of each radius. And this is a compilation of the measured dynamics of the stellar velocity as a function of radius. And for these dwarf galaxies, so we use like thousands of stars in those galaxies. And again, the same story here as a function of radius. The mass density inferred from the dynamics is solid line. Solid lines, there are many solid lines. On the other hand, if you take into account the stars and gas, that's what you call the baryonic density, is far more smaller than the total mass that we inferred from dynamics, right? So that's another evidence of the dark matter. So we have some invisible matter that contributes the dynamics of stars in the dwarf galaxy and stars and gas in the galaxy and galaxy in the galaxy cluster. Those are the firm evidence in astronomy about the existence of dark matter. And these invisible matter, on the other hand, however, we know that they cannot be baryonic matter, and that evidence came from the CMB. So measured anisotropy of the cosmic microwave background sky is about 1 part in 10 to 5. Okay, and then we know that amount of anisotropy was at when universe was 1,000th of current size, or the redshift of 1100 about, yeah. But then we also know that from the linear perturbation theory, the density perturbation can only grow proportional to the redshift or the scale factor, right? So the linear density contrast from the CMB up until now can grow only by a factor of 1,000. So if you multiply delta T over T that we observe from the CMB sky, which is 10 to negative 5, to 1,000, what you get is about 0.01. on the scale of galaxy cluster, which means that the galaxy cluster would not form if what you see from the CMB anisotropy were the only perturbation we had in the universe, right? So there must be another component in the early universe that create the hot and cold, the dense and sparse spot, like the density fluctuation that is far greater than what you see in the CMB sky. So that's what CMB can tell us, which means that dark matter, previously I named it as invisible matter, cannot be baryonic or cannot interact with baryons. Okay, so that include, for example, the planets or us as a component of dark matter. I mean, in terms of astrophysical properties, we don't shine by ourselves, and then so does our planet. So the Earth or us, we can be some part of dark matter, but we cannot be 100% of dark matter. Okay, so now the astronomical evidence for dark matter comes from the black cluster. So here we see the three different objects on top of each other. So we see first the location of galaxies here as an image, and also the bluish spots are the distribution of mass traced by gravitational lensing, and the red spot is the distribution of X-ray gas, hot gas traced by X-ray. Okay, so this is black cluster because we have two clusters, and the small cluster is hitting the large cluster with high velocity. That's why it's called black. And then what's clear is that the distribution of total mass is following the distribution of galaxies, not the gas, right? So gas are stalled in the middle because they are interacting very vigorously. On the other hand, the galaxies and gas and total mass in the cluster, they are not interacting very much. So from this observation, we can constrain the self-interaction cross section, or sigma over m. And basically, we are constrained n sigma, but then the number density, if you know the distribution of mass in the cluster, is basically a proxy for the 1 over mass. So in terms of fundamental properties, we can constrain the sigma over m less than 1 centimeter square per gram. So those are the astrophysical evidence of dark matter. And then we can think of the possibility that dark matter may be interacting with a standard model particle. So in that case, we can expect some in direct detection, or we can just expect some recoil event of dark matter, bulk of dark matter of the standard model particle, but then we still haven't had any detections, right? So that's the status of what our knowledge about dark matter. So we have some limit on the interaction between the standard model particle and dark matter, and then we also have some limit from the observation, the astrophysical observations of what dark matter properties can be. So here I'll add one more observational evidence, or the one more possible astronomical way to study the properties of dark matter using the LBK gravitational wave observatories. The LBK is acronym for the LIGO, Virgo, and Kagra. So here I show two pictures of LIGO detectors and one Virgo detector, and then Kagra is one in Japan. I don't have a picture for that, but then Kagra joined, and I think Kagra was in operation, maybe not in the 100%, but from O3b, that was in the, I think, last year. Okay, so this LBK consortium, they have announced the complete list of compact objects in their O3b run, and those are the distribution of the black hole binaries, or the neutron star binaries, as a function of time from left to earliest to the right, the later events. So there are so many events, but one thing that you can notice, and there are no events less than this bar. So this bar, I plotted something around the 1.4 solar mass. That's called the Chandrasekhar mass. Is that why is that? That was the question. Is that because we don't have, is that because our instrument is not sensitive enough to detect those small black holes? The answer is no. So here, what I plotted here is as a function of frequency, the power spectral density, the sensitivity or the signal for the LIGO detectors. So here, this red line here is the noise curve for the advanced LIGO. Here now means as of 2018. So I think at the moment it will be in between these two curves because this purple, the magenta line is the advanced LIGO at its full upgrade. And this bottom line is the sensitivity curve or noise curve for the Einstein telescope. And to compare those signals, to compare this noise curve, I plot also 3 signal curves. So what's on top is 10 solar mass binaries. So 10 solar mass, 10 solar mass binary. In the middle is 1 solar mass, 1 solar mass binary. And then the bottom is 0.1 solar mass, 0.1 solar mass binary. As you can see, obviously, for those small black holes, mass less than 1 solar mass, our current advanced LIGO detector can detect those binary signals, right? So it's not the limitation of our detector. Of course, we have to put those black holes binaries in the nearby. So this signal curve, those 3 are all created by assuming that that binary is in 1 megaparsec distance. So as we are focusing on the lighter black hole, we can only reach out to the local radius, so it's the smaller volume. Maybe that may be the reason why we haven't heard from those small black holes so far, but there's the limitation of the instrument. So this is another way of looking at this, the same thing, as a function of component mass. So assuming the equal mass binary. So we plotted the horizon distance. That's a distance below which we can achieve a sigma detection of this the black hole binaries of this mass. So if we are focusing on the 1 solar mass binaries, we can reach out the coma cluster, the cluster that I showed earlier in this talk, which is about 100 megaparsec away. And then 0.1 solar mass, we can reach out to about Virgo cluster. That's the cluster that hosts M87, the famous supermassive black hole. And 1% of solar mass, we can go to Andromeda galaxy, right? So those black holes may exist, and then we have a facility to hear the coalescence signal of those black holes. But then why didn't people consider that? Or what could be the reason that we don't see that? The reason is because of this fundamental limiting mass of the black hole in the cellular evolution theory. So this is one summary plot that I took from Kipson's book, Black Holes and Time Warps, as a function of the size of star and the mass of star. And this plot shows the destination of the star when it consumed all the fuel, hydrogen fuel at the center. So if the solar mass star ran out of the hydrogen fuel at the center, it'll no longer be supported by the hydrostatic equilibrium from the pressure generated from the thermonuclear reaction. So the star will contract, getting smaller and smaller and smaller until the star will be supported again by the electrons degenerate pressure. That state we call the white dwarf. If the star has mass twice as heavier than the sun, and one of the examples is Procyon, and assuming that this Procyon would not lose any of its mass, but just lost this fuel and then contract, and then it'll pass the regime for the white dwarf, and it will be even smaller and smaller, and then all the protons will capture electron to be neutron.
Sorry, Donghui?
Yeah.
Could you explain the slope in the previous slide? Slope of the line in the previous slide.
This slope?
Yeah, it looks like some power law, right? And
yeah, it's a power law. Yes.
What is the exponent of this power behavior?
I think this combination of how loud the binary black hole would be for a given mass, and then basically is the distance square, right? So we can
Is it square? It's unclear. I mean, okay.
Distance square. Okay. So as we go further away, the flux is diminished by distance square. But then as you are looking at the smaller and smaller black hole, and then the signal, the loudness
the slope is not, it looks like not precise the distance square. So that's why I'm asking.
No, it's not a square. I mean, it's the combination of distance square and then the mass dependence of luminosity.
Okay. Some additional powers. Okay.
Yeah. And then and then we also integrate over the frequency range. So that's, I mean, it's a combination of all those.
Thank you.
Okay. So, and then heavy stars will end up as a neutron star, right? And then even heavier star will end up in the black hole. So even though we don't know exactly what's the maximum mass of neutron star, but what we know is that there's a Chandrasekhar mass limit below which all the star will end up as a white dwarf. Okay. And if you look at this equation for Chandrasekhar mass limit, it's a very interesting equation because this equation only involves in two parameters. One is the fundamental physics parameter, the Planck mass. Another is the proton mass, which is by no means fundamental. But if you combine these two mass scale, so 10 to the negative 5 gram with the proton mass 1 GeV, and that ends up giving us a solar mass, which is the Chandrasekhar mass. And the key observation here is that Chandrasekhar mass is very far from the fundamental property of nature. It's a property of our standard model. So if you have some middle world, like in dark world, which can have some heavy proton kind of particles, and then for that dark matter world, this Chandrasekhar mass can be very small, smaller than 1.4 solar mass. And that was the basic starting point of this project. Okay, and then that's the way that we can cook up the small mass black hole binaries from the cell evolution, but not in our usual cell evolution, but the dark matter cell evolution. Okay. Then to realize that, I need a little bit more complex structure. Okay. So what I do in summary is that just instead of having just one boring species of dark matter, I introduce something like dark proton, like X particle, dark electron, like C particle, and then dark photon, I call the gamma D. The reason why I do that is I need some new property of dark matter. Namely, I need dark matter to dissipate its kinetic energy. So in this theory, we have 4 pre-parameters: the mass of dark proton and mass of dark electron, and then the coupling constant of the proton and the electron particle, and then the temperature of dark matter particle. Because we know the semi-temperature, we parameterize the temperature by C. That's the ratio between dark matter photon temperature and then CMB photon temperature. Okay. The reason why I need this is I need them to form a bound state to lose kinetic energy, or in terms of the jargon, inelastic collision. The logic is simple. So if you think about the standard structure formation model, at the very early universe, when the halo was first formed, we have dark matter halo, and the baryon particle altogether was just in this big haze of halo thing. But at the end of the day, something happened to baryon, and that didn't happen to dark matter. So we ended up having this big dark matter halo hosting a small galaxy at the center. And that thing that dark matter didn't do, but baryons really did, was a cooling and losing kinetic energy. So by losing kinetic energy, the baryonic particle can sink toward the center, right? And then form interesting objects like galaxies and planets, or the gas and like us, okay? This model of atomic dark matter is not new. And in fact, Lisa Randall, she had this theory of atomic dark matter. And then what she did was that she tried to cool this dark component to form a secondary disk structure on top of our usual galactic disk to explain the periodicity of the strong gravity, which may participate in the extinction of dinosaurs, as she wrote this textbook. Although in that primary reason, her model was excluded by the fact that we didn't see this acoustic oscillation in the dark matter power spectrum. That was the unavoidable consequence of that parameter space. But in our model, we are shifting the parameter space, focusing on the small object like black holes. So we are leaving the different parameter space. It's not yet excluded. Okay. So just like what I said, if you have dark proton, dark electron, and dark photon, just like we have normal CMB recombination, we expect to have dark matter recombination, below which or beyond which the dark matter particles are basically neutral. Okay, and then for a given 4 parameters, dark proton mass, dark electron mass, and dark CMB temperature, and the coupling constant, we can calculate the recombination history and the last scattering surface of dark matter. And that's very interesting. And also we can extend this a little bit further to figure out the typical size of the compact dark structure, dark matter halo in this atomic dark matter model. Okay. But one constraint that I required is that because now we observe large scale structure with the cosmic web and then cluster and then void, so we don't want to spoil the observed cosmic large scale structure. So the requirement is that for the dark matter halos heavier than 10 to 11 solar mass, that is like 1 order of magnitude smaller than our own dark matter halo. For those dark matters, the cooling time, the means that energy dissipation efficiency is far less efficient than the age of universe. So it means that cooling doesn't happen for those heavy halos, but cooling can efficiently happen for the small halos. That's the requirement, okay? But then if you think about this formation of dark compact object using the dark atomic model, this formation process is exactly parallel to the formation of population 3 stars or the first stars in the universe. So when you form first stars, we only have hydrogen in our standard model, hydrogen and helium, and then we try to form the stellar object based on that, right? And then what I did was just transform this, just to take the result of this rich pulsary star formation literature and then rescale those parameters, because once halo is formed, and then it's realized, and we forget about our former memory, right? That's what I mean by thermalization or visualization, right? And then after that, things must be self-similar, because after that, what's acting is just 1/r² gravity with the electromagnetic interaction. So there are so many interesting and rich physics of the rotation and then shock and fragmentation, but we assume that whatever standard model particles will do to form first star will happen same way in the dark matter sector, okay? So in that way, so what you can do is just take the population 3 star simulation, the first star simulation, and then rescale all the physical parameters based upon these 2 mass scales. One is the Chandrasekhar mass scale, I explained it earlier. Another is the opacity limit. That was the old calculation by Martin Rees or the Rindenbell in 70s. This is a limiting mass where the cooling is no longer efficient, okay? So the story goes as following. So if you have the cloud of gas that's cool and collapse and collapse and collapse, while this collapse, its density is increasing and increasing and increasing, right? When density increases, what happens is that its opacity is also increasing. And then there might be some critical density above which the photons cannot escape, simply because there are so many neutral atoms around it and it will absorb the photon. In that case, the system cannot lose energy. So there might be some fundamental theory limit of how small the stars can be. That's the opacity limit, okay? So we calculate the opacity limit of pulsary star, which is about 1,000 solar mass. That's about the ballpark of the mass of ballpark mass of a pulsary star. Then we rescale this opacity limit also according to the mass of proton and then temperature that we can reach. And then that temperature is given by the energy gap in the dark molecules. Okay, in the pulsary star formation, the crucial coolant for that provide the cooling is the hydrogen molecules. In the same way, we assume that for dark matter star formation, the crucial energy scale is set by the ground state and the first excited state, which is the rotational state of the dark hydrogen molecules. And then we can also calculate the energy gap in terms of physical parameters like a fine structure constant, proton mass, and electron mass. But we scale that value to figure out the mass scale, right? And then what we have is we have the distribution of mass in the population 3 star, and we just simply rescale them by using the different opacity limit. Okay. So here's the result. So we have the mass function of dark black hole that can form from the atomic dark matter model. So I draw 4 example lines. They're all subsolar mass here. And then the green is for the 50 GeV dark matter proton. And as you increase the proton mass, then you decrease the mass range. Okay, so 200 GeV can predict like 1% to like above the solar mass. So those are they have same slope because I took the slope from the Popsy star formation and then just rescale them using the proton mass. Okay, and I can also find is the statistics of Popsy binaries, right? And then by binaries, what I mean is I have the ratio distribution of the heavy mass, heavy star and the light star, and then the semi-major axis distribution and also spin distribution. All of these things is known for the Pop3 star simulation. And then what I can do is translate that into the lingo of the gravitational wave detector, in which case this mass scale called the Church mass scale is very important. So what I can also plot is the distribution of Church mass as a function of the number density of Church mass. And then I can also translate that into the horizon distance of detecting those particles and those black holes, right? So if you focus on the 10% of solar mass black hole using LIGO, advanced LIGO, as I said, you can go to about 10 megaparsec, which is about to the distance of Virgo cluster. But using the Einstein telescope, we can extend it further to the 1 gigaparsec, is a truly cosmological scale. Okay, then from that we can also calculate the event rate as a function of proton mass and electron mass. And then we also have Chandrasekhar mass. As I said, as you increase the proton mass, Chandrasekhar mass can be smaller and smaller. And it turns out that for this parameter choice, the opacity limit, the minimum Jeans mass is actually always bigger than Chandrasekhar mass, meaning that whatever we form, the star, and that must be a black hole. So but that doesn't necessarily be the case, but this turns out to be the case for these particular parameter choices. And what's interesting is that for the advanced LIGO current and the full, we expect, depending on the fraction of black holes in the total dark matter. I mean, this is very analogical to the fact that not all baryons we have ended up in star, right? So we have some fraction of baryon, some fraction of atom locked in the star. So that fraction, we also treat them as a free parameter. And then if you say that's 10 to negative 3, then that's optimistic case. 10 to negative 5, that's a pessimistic case. Depending on that, we expect some couple of event even for the current LIGO, right? If our proton mass is about 16 GeV and the electron mass is about 100 keV. I mean dark matter. Okay, so that's the prediction. And then we look at the data set and then see if there's anything we can do with the current data. And then there are 2 noticeable small black hole pairs. One is GW17 or A17. That's the famous Kilonova one, so we cannot do anything about it. So, so we skip that. But then another one is 190425. Sorry. That's another black hole binaries, or neutron star binaries. We don't know what it is, but then we don't have electromagnetic counterpart for this observation. Okay, the mass range is between 1.5 to 2 solar mass and 1.1 to 1.6 solar mass. And this can be neutron star, or neutron star black hole, and black hole. The official statement about in the LBK collaboration is that this object is neutron star binary. But just to trigger an interesting discussion, if this were neutron subbinaries, this is quite an oddball, right? This is a distribution of total mass of neutron subbinaries, and the left-hand side is a distribution that combining all the neutron subbinary we have seen so far in our Milky Way. And this is the distribution of the total mass of this particular event, right? And they're clearly quite separated. Of course, that's under the different selection. Those neutron subbinaries that we observe from the X-ray or some electromagnetic counterpart, and this one doesn't have any electromagnetic counterpart. So maybe this can be a different population. That's true. But just to stimulate your thinking, I just show this plot. And if this were really a black hole binary, one possibility is that this black hole binary might come from the primordial black hole. Okay, I mean the primordial universe. We happen to have a very large fluctuation that can collapse into a black hole that can form a binary. Okay? But then there's interesting observation from this paper, Chen et al. 2020. And if we form the primordial black hole with this mass range, okay, and at that time, I mean, then we need very large fluctuation of scalar perturbation, okay? And that large scalar fluctuation should also create the gravitational wave in all the universe. And that gravitational wave can propagate all the way to us. But at that time, but during the time, this must be redshifted. And then this redshifted gravitational wave created from the primordial universe is fall into range that we could see in the pulsar timing array. But nanograph, the pulsar timing array experiment in the US, in 11-year data release, they didn't see any concrete evidence for the gravitational wave of that frequency. Based upon that, we can have a 90% upper limit of the primordial black hole fraction in that mass range, which is far below 10⁻⁵. So they may not be a primordial black hole. So we enjoy this possibility and then ask ourselves, what if this object, GW190825, is a dark matter black hole binary, right? Just from single object, if that turns out to be the object that I'm interested in, what you can conclude is that we can rule out the heavy dark proton by 99.9% CL. So dark proton mass must be greater than 0.96 GeV. Okay. Of course, if it's not the dark matter black hole, we can constrain the fraction of dark matter black hole in the dark matter down to 10⁻⁵ level, right? Because in our pessimistic scenario, we expect that 1 or 2 events from the current LIGO. And our study get some interest from the LBK collaboration, and then Sarah and I, my collaborator Sarah Sandera and I were invited to be their MOU partner to interpret the small mass black hole searches. So this is the official paper by LBK. I mean, my 1,500 collaborators, and then myself and Sarah, that's in the archive. And then our official statement is that this event is not a dark matter black hole, and then in that case, we have a limit, okay? So this is this is the main point. This is interesting observation that if you have small black holes, they can form if not primordial black holes. I think that has some strong evidence for it. And then it can be a dark matter black hole. And if it's dark matter black hole, we can constrain the property of dark matter by looking at this population spectrum of those black holes. If we detect them, that's great. Even though we don't detect them, we can constrain as a function of minimum mass, its fraction. And this minimum mass and fraction diagram can be also translated into 2 things. First of all, their mass distribution, because Chandrasekhar mass can be also constrained. And second is the property of energy dissipation, right? So if you think about the state of 2 particles that can interact via electromagnetic interaction, they can have like ionized state or the atomic state or the molecular state. And then the state that they can have can be a strong function of temperature. So as a function of temperature, we can quantify how efficiently can they lose energy. That is called something called the cooling function. Okay, so here is the one example. We have a temperature, function temperature from 10 to 100 Kelvin to say 10 to 8 Kelvin. So if you are thinking about the dark atomic dark matter or dark proton electron in the very high temperature, they might be in an ionized state. Just like in the cluster, we have X-ray gas in the cluster, right? In that case, we are constrained from the cluster, like bullet cluster. And if as you think about the lower and lower temperature, we're thinking about smaller objects like galaxies or the dwarf galaxies, right? So for dwarf galaxies, I mean, sometimes if they're so vigorously interacting that we can destroy those galaxies, right? Or I mean, then maybe that's one of the reasons that we don't see as many dwarf galaxies that we supposed to see in the simulation, or this is bound from the fact that we need to form those galaxies at redshift 10, for example, something like that. So we can, it's not just the gravitational wave detection. We can also play this game by combining other astronomical observations into this plot, so-called cooling function. I mean, or how does the cooling efficiency change as you change is quantum states. Okay, and then from the first principle, also we can calculate the cooling function as a function of temperature, at how efficiently they can cool for a given the 4 parameters: proton mass, electron mass, and then the constant, right? Those are the examples, and then we can also have the phase diagram as a function of number density. So when the first structure collapses and how their temperature changes. And those are the typical input that we need to run end-to-end simulation of this thing. I said earlier that I just took the result from the POP3 simulation and then rescale them. I don't have to do it, right? Because now I have this phase diagram as well as detailed atomic and molecular process rate. I can actually go and run the embodied simulations, right? So that's what I'm doing currently with my students. And then here we revise this earlier plot that I showed, this cooling time and then collapse time, the age of universe argument. We revise that by including the detailed chemistry and following the gravitational evolution of the individual halo. And that's what I have some fun these days. Okay, so I hope you enjoy the new possibility to study dark matter, in particular dissipative dark matter, using the new astrophysical facility, the gravitational wave detectors, and then just having single event can imply a lot about the dark world, and in particular about the zero solar dark proton mass, and also about how it'll dissipate its energy as a function of its quantum state or temperature. Thank you very much for your attention, and I'll take any questions.
Thank you for the very nice talk. Yeah, question, Professor Chung-Ang.
Hi. This is quite interesting. I enjoyed your talk again. The main ingredient of this idea is that is adding some atomic structure to dark matter to form a black hole.
Yeah.
And we heard many talks about dark matter described by effectively by scalar field. So, and I remember Chaptik did some work about the scalar field collapse, and depending on some critical value, it could form a black hole. So I wonder whether that if we use that idea or that result, then what will be the implications in this dark matter binary formation and the gravitational wave observations?
Okay, so first of all, scalar field, the bosonic field, right? So for the bosonic particles. So this Chandrasekhar, I mean, there might be some similar thing as Chandrasekhar mass. And in that case, I think what people does is comparing the de Broglie wavelength or the Compton wavelength to the Schwarzschild radius. In that case, instead of this cubic power, we have square power, so without any interaction. So if you have bosonic particles without any interaction, it's square. So instead of solar mass, this bosonic black holes, like instead of fermionic black holes, will have 10 to the negative 19 solar mass. That's what I remember. That's very light. Yeah. But then if you can also, on the other hand, you can make this mass larger by introducing some interaction. So if you have quartic coupling, for example, that, I mean, giving the extra repulsion of the bosonic sector, then you can have something like solar mass type Chandrasekhar mass. So it can be comparable, but I'm not sure about other structure like atomic and molecule. So molecular properties. So for example, in this very model, I like this model because I can enjoy the pre-calculated quantum mechanical the event rates, right? And then I know what are the transition rate, the Einstein A coefficient for the hydrogen molecules and hydrogen atoms, but for bosonic particles, that may be a little hard. So we may be more phenomenological, but I think, yeah, my answer is that without any interaction, bosonic black holes will have very light mass. So if you are to increase the mass, then you need to add some extra interaction. And secondly, we don't have this parallelism. So, but certainly it's possible, yes.
Thank you.
Any other questions?
I have a question.
I have one question. So do you assume the standard model sector and dark sector interact only through the gravity?
Yes.
So
yes.
you turn off the kinetic mixing in the dark photon.
So, yeah, I didn't assume. I mean, this one again is the bottom-up approach. So I didn't need any interaction between. Of course, that kind of interaction can be there, but for now we don't add them.
Can I ask?
I mean, did you have a question?
Yeah. So you have a dark photon. Is dark photon precisely massless or it's massless?
Yes. Here we assume massless, just like standard model photon.
I see. So then you
Long
said
range.
I see. So then you also have a dark matter disk in your case because of dissipation.
We can have dark matter disk. Yeah, but I think we will have more of the small dark matter clump than dark matter disk because we try to avoid dark matter disk because that reason was included by observation. I think one critical difference between Lisa's model and my model is that we assumed a very cool dark matter. So the temperature of dark photon is very low. So cooling happens very early on. I mean, the recombination happens like relative millions in the very early universe.
I see.
So Donghui, how essential is the masslessness of the dark photon? It should be like that to have dissipation?
No, I don't think so. And typical energy gap is like order EV. So I think we can accommodate very, very light mass, I can assume, yeah.
Okay, so
but
you
have, yeah.
Okay, so electron board can be possible, you think?
I think the self-electron board, as long as it doesn't spoil the normal atomic processes like radiative decay and then all those things, it's fine, yeah.
Okay, yeah, Pyonghwan and others are also pointed out there could be the portal interaction. So there can be the visible dark sector communications. Then probably we can learn from your approach to those the portal interactions, right?
Right. Yes. Certainly we can do it. Yeah. But here the focus is the spectrum of the black holes. I didn't think much about that, but yeah, that's certainly possible. Yeah.
Okay. Yeah, thanks a lot.
I also have one quick question. So can the dark proton be very light so that the dark black hole can be very heavy, out of LIGO reach?
Yes. I mean, that's certainly possible. Yeah, I think we were talking about this possibility a couple of times, but we didn't have concrete idea. But I think if that's the case, what I can make is the theory about the first quasars or the supermassive black hole.
Yeah. Ah, okay. I see.
It's another mystery in astronomy. Yes.
Oh, I see. But they have to form after CMB, right? Because CMB.
Yeah. We don't want to spoil the CMB. Yeah.
Okay. Well, interesting.
Because they will have a great giant accretion disk that can spoil CMB. Yeah.
Well, it's an open possibility.
Yes, it's a fun possibility. Yeah.
Any other questions? All right, then let's thank Professor Donghui Jeong again.
Thank you.
Thank you. And Professor Jihun Jim. Okay, so
yes.
Our second speaker is Professor Jihun Jim from Seoul National University. He will tell us about solving the mysteries of supermassive black holes in the era of high resolution simulation. So please start.
Yeah, can you hear me?
Yes.
Yeah, thank you very much for the introduction, and thanks for inviting me to present at this great workshop. I really appreciate it. And so I'm a computational astrophysicist, and I was asked to talk about, and I'm planning to talk about our understandings and the mysteries surrounding the supermassive black holes from the perspective of a standard contemporary astrophysics. But what happened to supermassive black holes, how it came to be, how it came to have such a large mass could be an interesting topic for this particular audience. I mean, Donghui just talked about it briefly, but not just because the growth history of the supermassive black hole has been driven by mergers. So, I mean, in some cases, in many cases, so it gives a context for the gravitational wave signals that we're interested in, we're talking about, but also because the huge mass of supermassive black hole itself allows us to think about what kind of physics we might have missed, or what new physics we may consider, such as what Donghui just mentioned. So I'll talk about more or less sort of a standard perspective, standard approach in dealing with the growth of supermassive black hole and how we want to tackle the problem using computer simulations. But I hope you to think about what new physics you may want to bring in, you may want to consider, something that I hope you to do. So these are the outline of this talk. So I'll just go right in. So there are two different population of black holes. So one is, as you can see, these are the probably the famous pictures that you already know well. So if we were to draw a sort of black hole population in the this plot, so x-axis is the black hole mass in logarithmic scale, the y-axis is the black hole count, and you can see that there are two peaks, two known populations to the humankind. So one is the stellar mass black holes, say hundreds of solar masses. The other is the supermassive black hole population, above million solar masses. Then it's postulated that at least one supermassive black hole exists per galaxy. I mean, that's been known by observations and by the contemporary theory. So, I mean, again, these yellow peaks are known by the LVK gravitational wave detectors, and the blue ones are include some of the famous ones, such as the Sagittarius A supermassive black holes. So, as the topic of my title of my talk suggests, I'm more interested in the supermassive black hole part of this population chart. But the obvious question that you may ask is, why is there a gap between these yellow and blue peaks of course, obviously there are some observational constraints. We don't have yet a good eye to look into those ranges, say between 1,000 to million solar mass ranges, because that's not covered by any of the detectors or telescope of the mankind. But because that range is empty at this point, some of the questions that's being raised is like whether these two types of black holes, stellar mass black holes and the supermassive black holes, are of the same origin, or do they start from a completely different starting point, different origins. So these are the questions that can be immediately raised just by looking at the population chart, but also there's this problem of high Z quasars, high redshift quasars. So many of the supermassive black holes existed in the very early universe, like just hundreds of millions of years after the Big Bang. Not enough time, based on our contemporary physical knowledge, not enough time for any black hole to grow quickly. There's just not enough time there. So unless you start off from a extremely massive seed that could be created by some unknown physics or yet to be known physics. So this problem of redshift 6 or 7 quasars will become only worsen, I think, as soon as this new telescopes such as JWST starts to detect some very far away signals, because the JWST and the future telescopes will reach an even further away universe, and that will give us probably a chance to see similarly massive objects, similarly massive supermassive black holes that are farther away from us, and that will only complicate the problem of this high Z quasar issue. So the supermassive black hole mystery, especially at high Z, I mean, there are questions that can be raised, and then I'm just going to talk about only 2 of them. So what were the supermassive black hole seeds? And that's the first one. And the second is, how did these supermassive black holes grow so fast? So the first question, what were the seeds? I mean, there were traditionally 2 different ideas, but lately the third one is coming. So the first one was the most typical idea, most contemporary idea. That's the death of massive stars, the first generation stars in the universe. So they tend to be massive and large, so they live quick and die fast. So that leaves a remnant of say hundreds of solar mass black holes, and that remnant black hole could be the seed for supermassive black hole. But as I said, because it takes such a long time for it to grow up to a 10 to the 6, 7, 9 solar mass black holes, people have always been searching for a different seed scenario. So for example, the second scenario that they are talking about is the direct gas collapse of a black hole. So the scenario says that there exists, let's say, 10 to the 5 or 10 to the 6 solar mass primordial gas clump in the early universe. And for some reason, it never fragmented to form stars because of, for example, the background radiation. The radiation is coming from the nearby young stars. So the gas cloud just is warmly heated, but never form a stars, never fragments. But then suddenly it starts to collapse to form a single giant black hole, such as of mass 10 to the 4 solar masses. So these are just another sort of idea to bring the seed mass closer to the supermassive black hole range. So you can see that here, the second idea already talks about the possibility of these 2 populations of black holes, stellar mass black holes and the supermassive black holes, have different origins. They grow out of completely different seed. I mean, this is just the second idea. And the third, more recent idea that people are talking about is the successive mergers that could happen at the center of a really compact, dense star cluster, such as the nuclear star cluster that exists in many of the galaxies. So in these settings, if there exists a really dense star cluster, the density of the stars and the subsequent black hole populations are so dense, so high, that the merger rates of the black holes are high enough that in just about hundreds of millions of years, you can form hundreds of solar mass black holes or up to thousands of solar mass black holes. That has been shown by recent study using a Monte Carlo calculations and semi-analytic calculations. So this allows us to think about a context that is probably not common, but context that a massive black hole seed, massive supermassive black hole seed, a possible ancestor of the supermassive black hole, could have formed in the early universe in a dense star cluster. So I talked about 3 different scenarios of what the supermassive black hole seed could have been. And the second question that I raised for the about the existence of high Z supermassive black hole is how did they grow so fast, even with the sufficiently large seed mass? You have to grow it to 10 to the 8, 9 solar mass black hole, and that's a lot. I mean, it's a massive, small galaxy, small dwarf-sized galaxy, and it's not like the black hole can just go around and eat up all the gas or stars inside the galaxy, because the black hole is not so, it's not that easy for it to move around, right? I mean, so usually what people think is that somehow the gas or the fuel for the black hole has to be drawn in to the center of the galaxy, where the black hole usually sits. So for that, you have to clear many different hurdles. For example, stage 1, supermassive black hole has to grow up to a 10 to the 8, 9 solar masses. So that much of a mass, equivalent of a small dwarf galaxy, has to be drawn in. So it has to be coming from outside the galactic disk, outside the galactic halo, to the center. And that's a non-trivial process. You have to calculate the number of mergers that each galaxy can experience, and whether it can reliably overcome the angular momentum barrier of the galactic disk and then somehow come into the center. It's not that easy. I mean, it's just first hurdle is already high enough. And the second, so that's the first story. So, I mean, oftentimes what people put as a solution to this stage 1 is a sort of giant, violent merger between 2 galaxies, 2 equal mass galaxies, and that completely disturbs the pre-existing gravitational potential and draws the gas inwards. So it could allow some chance for the gas to come right into the supermassive black hole. So that's stage 1. And then stage 2, even if the gas comes into, somehow finds its way to the black hole, it has to somehow suppress the star formation process, which is a competing channel. I mean, if you think about it, gas turns to stars, the stars become a supernova and explodes, and the gas just ejects away. It just explodes and sometimes escapes the galaxy. So if the gas turns into a star, from the black hole's perspective, it's a loss. You lost the potential fuel for it to grow. So that's something the competing channel has to be somehow suppressed. So that's the concern in the stage 2. And stage 3, even more fundamental. Even if you find a pocket of gas that's right next to the supermassive black hole, about to get sucked into the supermassive black hole, you still have to bypass so-called the Eddington limit, which is simple. So if gas, dives into the black hole's event horizon, it has to lose its gravitational energy, and there is no other way for that energy to go but to be radiated away. So you can actually estimate the energy that the infalling gas emits every time, say, a single proton goes into the black hole. You can estimate the energy that it has to lose, the gravitational energy that it has to lose, or the radiation energy that it has to emit. And you can actually calculate its energy, and it is actually quite high, that it actually makes the black hole the most luminous, one of the most luminous objects in the universe. The black hole itself is dark, but the accretion disk or the material that is surrounding the black hole is really bright because of this process, fundamentally because of this process. So this radiation actually gives the radiation pressure to the later coming material. So it gives it makes the negative loop. So as soon as one proton goes in, its radiative its energy, its radiation energy keeps the second proton to not go in. So it's a negative feedback process. So there is a fundamental limit there, and that's called the Eddington limit. And note that this is about the gas physics. I mean, any radiation that we're talking about will push the gas away, but maybe not some other particles, say dark matter particle or some dark sector particles. But let's not think about that here, but only if we only talk about sort of the conventional baryonic physics. And this Eddington limit is something that we have to overcome to really grow this black hole fast enough for it to reach a 10 to the 9 solar mass at 5 redshift 6. So these three stages has to be considered in any theoretical evaluation or any computational calculations. So intergalactic dynamics for the star formation and feedback process in the second part here, and the supermassive black hole accretion and feedback to explain the third stage. So given the time limit, my research has been focusing on this, the stage 2 and stage 3 of the black hole growth. But given the time limit, I'm going to only talk about the first part and briefly showcase what I have done in the second part. So I'm not going to talk about sort of the numerical details here, but all I'm going to say is that as a computational astrophysicist, we have a history of like 20 years or more of developing the code that can accurately describe the structure formation, the evolution of the universe, including the galaxies and the supermassive black holes, the embedded supermassive black holes. So for example, here you can see the two galaxies merge and the two black holes embedded in each of them also merge. And it gives makes this giant outflow, as you can see at in the bottom right, the picture at the bottom right. And also, I'm going to say that in my tools, I also included the radiation from the stars, the newly born stars that are right next to the supermassive black holes, another feedback source, not just the radiation from the black hole, but the radiation from the stars that are existing near the supermassive black holes. So here's one example of what I did. We choose a really massive galaxy at high redshift universe created inside a computer. So this high sigma peak, really dense peak, most of the other regions in this entire fake universe is doing nothing. It didn't even form any structures, but there is this one high sigma peak that had already formed a massive enough galaxy that can host a potentially massive supermassive black hole at high Z. So that's the target that we are simulating, and then we impose all the super high resolution and all the fancy physics that I just talked about, including the stellar physics and the supermassive black hole physics, such as the radiation from the stars and supermassive black holes. And we, and we run the simulation with or without some of the key physics, such as the stellar radiation. And this is what we found. For example, here, this is the run that we did with the stellar radiation and the supermassive black hole radiation. And you can see that here at the bottom, near the location of the black hole, supermassive black hole, marked with the black cross, you can see that the temperature or the photo heating rates around the supermassive black hole is really high, to a level that it's above 10 to the 4 Kelvin, sometimes 10 to the 5 Kelvin. So it's so high, it's high enough that it cannot form stars. The gas around the supermassive black hole has been heated up by the radiation of the supermassive black hole or the nearby stars, that the gas is, the temperature of the gas is so high that it can no longer form stars. I mean, to form stars, the gas has to first collapse, cool and collapse, and then the nuclear fusion process ignites. But then, but if the temperature is high, then the gas just stays like as is, and it never fragments, never collapses to form stars. So as you can see here, the x-axis is the distance from the supermassive black hole, and y-axis is just a measure of how suppressed your star formation is near in that region. And if you just compare the red line and the green line, red line is the one that we included all the fancy physics, the radiations, all the accurate physics, I should say, radiations from the stars and radiation from the supermassive black hole, whereas the green one is the, I would say, what people have been doing so far before this research, this work. And you can see that the star formation there is suppressed. And I said earlier that the star formation process is just a competing channel from the black hole's perspective. From the black hole's perspective, if the gas turns into star, you lost the fuel, you lost the potential fuel for you to grow. So if the star formation is suppressed, the black hole growth is enhanced. So here, what you're seeing is the as a function of time, how the black hole accretion rate changes, how fast the black hole grows. And you can see that the red simulation, the one with the accurate physics, has a enhanced growth rate compared to the green simulation, which is what people have been doing before this work. So you can, all I'm saying is that by fixing the stellar feedback, we are finding a way not to lose the gas along the way, but make the supermassive black hole grow sufficiently fast to explain the high Z quasar. So this is in line with many other works that are trying to find the route to a direct gas collapse to the supermassive black hole rather than fragmenting into stars along the way. So here in this previous work, they included some of the turbulence physics that prevents the star formation of the gas along the way. But I don't have time to go discuss in detail the other works, but that's that. So I'm just gonna briefly flip through some of the recent works, more recent work that I have been doing. So I talked about the stage 1 process. You have to, borrow, or you have to steal the fuel from other galaxies for your black hole, for your supermassive black hole to grow. So that happens through the galaxy merger process, or the galaxy, people use the word, you eat up the galaxy, you eat up your neighboring galaxies. So actually in the high Z universe, in the high redshift universe, the mergers were more frequent, very frequent, and the speed was even higher. The merging speed, the approaching speed was really high because it's a high Z universe, and the structure formation in the universe has been always bottom up. Small structures form first, and then they merge to form a larger and larger structures. So if you actually look at the history of growth history of the embedding galaxy, any of the host galaxies of the high Z supermassive black holes, it's a result of 10, 15 very fast high-speed mergers. As you can see, as a function of time goes from left to right, and you can see that the small galaxies form to grow a large galaxy in just about a few hundreds of millions of years. And that actually is shown in my simulation as well. So you can see that there's a target galaxy, but there is an incoming galaxy coming in from the top. And we can actually dye those incoming galaxies, color it differently, and see where those incoming gas ends up being after the simulation. For example, whether it would just, get eject away because it cannot overcome the angular momentum barrier, or whether some of it would actually make it to the center of the galaxy and into the event horizon of a supermassive black hole. And actually, this is the ongoing study and something I'm very excited about. And also, I talked about the mergers. I mean, the mergers being the driver of the growth of any host galaxy of the supermassive black hole. But the merger of two galaxies can actually create the system, what's called a star cluster. It's a collection of thousands, tens of thousands, millions of stars. And because the galaxy merger, the high-speed merger, can compress the gas, compress the intervening gas to a level that the density is high and it fragments. So it's a process that turns a large amount of gas very quickly into a collection of really dense star clusters. And as you can see here in this movie, two galaxies merge, and this is the remnant, and all the white dots are actually the collection of many, many stars created in this merger simulations. And I have done many merger simulations and merger-driven star cluster formation simulations. And these star clusters can actually be fuel for the supermassive black hole, because I mean, I talked about the Eddington limit, Eddington barrier, but the Eddington barrier, as I said, was only Eddington limit acts only on gas because it's about radiation pressure pushing the gas away. But if you somehow find a way to bring this entire, hundreds of thousands of stars right into the neighborhood of vicinity of the supermassive black hole, then it could be a really nice fuel for the supermassive black hole to grow by tidally capturing the individual stars there. So that's one of the other studies that I'm interested in. And as I said earlier, the star cluster can also be a nursery for the supermassive black hole seed by successive mergers of the individual stars. So these are the new simulations that we're doing, and I'll be excited to talk about its results in the coming months. So please stay tuned. So I'll just put this as a summary, and I think already past the time limit. So thank you very much. I hope this was a chance for you to think about the mysteries of supermassive black holes, high-Z supermassive black holes, and imagine what kind of missing physics, or new physics we could include to solve this mystery. Thank you very much.
Thank you for the very nice summary and talk. Any questions?
Yeah, I have. Have you considered the effect of dark matter in these simulations?
Not in this simulation. So we, for example, I didn't have a chance to talk about it. Sorry. So when you meant the effect of dark matter, what do you mean? You mean its contribution to the supermassive black hole accretion, or?
Right. I mean the growing rates of the mass of supermassive black hole.
Yes.
Due to the dark matter. I anticipate in that dark matter just passes easily. So that
Yes, right.
it resists growing the stellar mass around this kind of supermassive black hole due to the gravitational interactions, right?
Right.
So it may decrease the growing rate because dark matter just may just pass, and so there are mass distribution farther away, farther. So
okay,
I'm not sure if this effect is crucial or but
so
just,
all I can say is the following. So there has been some research of sort of estimating. I mean, there hasn't been like a numerical study, numerical simulations that includes the accretion of dark matter yet. Although, for example, our group and some other group, maybe one more group is working on to include the accretion of stars in the galactic context. So that's what we're doing. And I haven't yet disclosed anything about the new results yet, but it's the results are exciting. Maybe next time. But so far, only sort of an analytic approach has been done to estimate like how big of a contribution it could be if we were to include the dark matter contribution. So, and the estimate that I remember is that up to only up to 10% of the entire supermassive black hole mass can be explained by dark matter contribution. So it's really hard for dark matter to accrete as you expect because it's collisionless. It just passes through the vicinity of the supermassive black hole unless it hits the event horizon. Whereas for the baryons, where the gas, if one particle goes in, it somehow drags the other particle with it. So it's a, it's a fluid, right? I mean, so there's that difference. So that's what I can say. And yeah, so there hasn't been any other numerical study that looked into the dark matter accretion.
Okay, thanks.
Thank you very much for your question.
When you refer to the black hole mass, what do you exactly refer to? Does it include the mass inside the horizon only, or including accretion risk too? Maybe very basic question.
No, that's actually a really good question. So when I said, when I talked about black hole mass or the black hole accretion rate in this simulation, I mean, obviously I have to admit that we cannot resolve the event horizon of the supermassive black hole. I mean, even if the largest supermassive black hole that exists in the world, we cannot resolve its event horizon because we want to both resolve. So let me say this. At the moment, what we can do is resolve simultaneously the galactic radius, galactic scale, and the Bondi radius of the supermassive black hole, which is defined as the sort of influence of gravitational interaction. So inside that radius, black hole is the most dominant gravitational source above any other components such as gas or stars. So that's the Bondi radius. And that's all we can do. So assuming that the resolution that we have is the Bondi radius of a supermassive black hole, then the answer to your question is no, we're not talking about the mass inside the event horizon, but the objects that surrounds the supermassive black hole, but maybe bound to be consumed by the supermassive black hole at some point.
I guess that's also the mass that we actually observe from the kinematics or
yes and no. Yes, in many of the astrophysical telescopes, but not in, like, for example, the Event Horizon Telescope.
Yeah, that's right.
for which we can actually resolve the event horizon.
Great. Okay, thank you. Any other quick questions?
I have a quick question. You mentioned the James Webb Space Telescope. So how does it help for supermassive black holes? Is it discovering more supermassive black holes or some distribution, or what do you want to learn from the observation?
You mean like what do we expect
what do you
from the JWST observations in the future? It's unclear to me. Actually, I'm not like an expert in the observation or observational strategies or what the immediate plan for the JWST telescope time. But I mean, the current world record for the high Z supermassive black hole is at around like a redshift 7.5-ish. But you know, it has been going up ever since, like in the past decade or 2 decades. So it's been slowly growing from redshift 5 to 6 to 7, and with JWST, it'll only go up, and it'll only leave us with less of a time for the supermassive black hole to grow from the beginning of the universe. So the problem of the high Z quasar will get even worse. So that's the point that I like to make. And yeah, that's all I can say.
Okay, thank you.
May I ask another quick question?
Yeah.
I'm sorry. I wonder if the dark matter properties can affect your simulations.
In regard with Kung-Ang Gang's question, so the dark matter accretion.
Yeah, that's one thing. Yeah.
So I feel like I have talked about this when I gave a talk at Yonsei University.
Right.
But if you actually change the properties of dark matter, so there has been some studies, not just the standard dark matter, but partially interacting or self-interacting dark matter model, and re-estimate the accretion rates onto the supermassive black hole. And yeah, I mean, it can be used to constrain the properties of the dark matter. Non-conventional dark matter.
Yeah, I'm imagining PBH as dark matter. Then can there be any effects?
Yeah, sure. I mean, the primordial black hole can be used by some as a candidate for the supermassive black hole seed. But as I sort of said in my disclaimer before the talk, I only talked about sort of a standard picture.
Right.
So there has been some studies about the PBH being a massive black hole seed, and that's a sort of whole new interesting field that many people are working on. Yeah.
Okay. Thanks a lot. Thank
you.
Actually, last year there was a talk by self-interacting dark matter by Haibo Yu from UC Irvine. He talked about gravithermal collapse of the very large dark matter halo. He had to assume that there is a massive dark matter halo in the beginning, and it undergoes a gravithermal collapse due to the self-interactions. So yeah, but yeah.
I see.
Yeah, it may be related. Yeah.
Any other quick question? All right, then let's thank Professor Jihun Jim again.
Thank you very much.